So thanks for the introduction. I must say I'm pleased to be here. I really wish it was under different circumstances, but it is what it is. We made the very difficult decision at about 4 o'clock this morning to start load shedding from 9 o'clock. These things are never easy to do, but it's a necessary evil. And I think, you know, I've got the next hour to try and explain to you some of the nuances and some of the complications around load shedding. I certainly won't be able to take away your anger by the end of this presentation, but hopefully I'll be able to ease just some of the frustrations. And then at the end, we can have some discussion during the Q&A session. I'm going to cover quite a bit of ground this morning. We're going to need to set quite a lot of context for understanding. And so I've phrased it in the way of certain questions. Firstly, I'm going to just give you a quick introduction to what a system operator is. And then try and get an appreciation for how big the problem is, because I think that a lot of people don't quite understand the numbers. We'll delve into those in a little bit of detail. We'll talk a bit around the 50 hertz and why supply-demand balance is important. And then I think we're going to spend probably most of the time talking about a national blackout. And the reason for that, you know, there's a very common phrase these days: what are you solving for? And I think it's important for us to get a really thorough understanding of what a national blackout is and how it's different to load shedding. And so we'll go into that. We'll talk a little bit about emergency reserves, and I think that's very topical. When we get there, I'll try and just give an example of how we got to where we are today. It's quite a useful example. We'll then talk a bit about how we actually go about managing this power system. Fortunately, because of the way we're running and have been running, the traditional methods of running a power system, planning a power system, no longer apply in South Africa. So I'll give you some of the methodologies and techniques that we've developed over the years to try and deal with this. And of course, this is not a one-man band. There are a lot of rules and governance that dictate to us how we actually go about load shedding. And so we'll talk a bit about that. And then finally, I've got just one or two final thoughts that I'd like to share at the end. All right, so let's jump in. Very, very sort of simply speaking, if you break down the Eskom value chain, you've got generation, who actually generates or makes the electricity. You've got transmission and distribution. They transport the electricity to the consumer. The difference between the two is really around the voltage. If you look at the transmission lines, you'll see the very, very large steel structures. Typically speaking, the larger they are, the higher the voltage. And so we'll see anything from about 275 kilovolts up to the highest voltage we run in the country is 765 kilovolts. Distribution, on the other hand, tend to be more regional, and they will then transport from the high voltage networks down to the consumer and actually into the office, houses, and the factories. And then, of course, we have our customer services that actually do the sales. In order to keep all of this stable, we need to have a centralized control. And I think this is the first key takeaway that everybody needs to very clearly understand. Bulk electricity cannot be stored. It must be generated at exactly the same time that it's consumed. Now, there is a bit of a caveat to that, and I'll go into pump storage just now. But for the most part, we simply can't store electricity and then, you know, release it on demand. And so what we have to do as a system operator is, for every minute, every second of the day, we then control and dispatch electricity exactly as the consumer are needing it. The easiest way to think about a system operator really is then to say that we are the electricity transport and distributor of the entire supply chain, and we oversee that 24/7, 365. Right, so being a very high voltage network, and of course, you know, moving around significant amounts of power, there are many safety concerns. And as I've just said, we have to have the centralized control in order to manage the supply-demand balance. And so in the industry, like with all the industries around the world, we have a very hierarchical structure. At the top of the structure, we have the National Control Center. We are currently part of transmission. I'm sure many of you have heard that we will be separating the transmission company, or the transmission entity. We're still hopeful that that'll happen by the end of the year. For now, it will be a subsidiary of Eskom, but it will be a legally ring-fenced company, and the system operator and the National Control Center will then be part of that national controls, that transmission structure. At the top, we have the National Control Center, who is responsible for the overall well-being of the entire grid. We also operate parts of the network in Swaziland. We operate parts of the network in Mozambique. And of course, we then have a very close connection to the power stations. Below that in the hierarchy, we have our distribution or regional control centers, including the municipalities. And typically they would operate networks of about 132 kilovolts down to around about 66 kilovolts. One of the things that has happened more recently with the introduction of renewable generation and with some of the IPPs now who are obviously embedded in the lower voltage networks, they are now getting a taste of how to manage generation. And unfortunately for them, it's renewable generation, which tends to be variable. At this stage, they're not dispatching the generation, but in the very near future, we see that it's going to be necessary for them to start interacting a lot closer with generators and actually start dispatching some of those power stations and controlling them more actively. Below that in the hierarchy, you then have very much the localized controls. This would be maybe down at a city level or at a suburb level, where you have your reticulation control. And we have this very strict hierarchy, as I say, for safety reasons, first and foremost, but also so that we have centralized control. When we give instructions for load shedding, the instruction comes from the National Control Center. It gets passed down into the regional control centers, who then pass it down onto the municipalities. And then the instruction is actually carried out by the regional and local control center. Contrary to popular belief, there isn't actually a big red mushroom button in national control that we hit to start load shedding. It's a lot more systematic than that. This is what the control center looks like. Here is Simmerpan in Germiston. You can see we have different desks that are carrying out different functions. And very broadly speaking, we have 4 functions that we carry out at the control center. The first is really dispatching the available generators to meet the demand, and that's our primary role. And we'll talk a bit about supply and demand and why it's so important. But you can imagine that if you have too much demand and not enough supply, in other words, we don't have sufficient generating capacity, we then start to put the network in jeopardy. The way it actually works is that if you don't have sufficient generation, your whole power system starts to slow down. We measure that in the frequency. So typically we should stay at close to 50 hertz. When we don't have enough generation, as is the case at the moment, the frequency then starts to drop, and that brings with it all kinds of complications. So I've reluctantly had to add an extra bit in the supply and demand part there, which says that when we don't actually have enough capacity, we reduce the demand to match the supply. And that's just a very polite way of saying load shedding. We also, of course, look after the transmission network. We have a very vast transmission network in South Africa. We're interconnected all the way from Cape Town up to the DRC, and from Namibia all the way across to Maputo. So we are part of a larger grid. That grid is all running at synchronous frequency. So your frequency in Windhoek, Pretoria, Maputo, Harare, Cape Town, all running at the same frequency, all interconnected, which gives us a lot more stability. The bigger the grid, the more stable it tends to be. But it also does mean that we're all locked in and share the same fate. We then also control the power system, and particularly when we do have incidents, there are a number of environmental factors that could impact the transmission network. And when the transmission network fails, then of course we have to put that back together. I think first and foremost, we are responsible for overseeing safety of people and plant. That's one of our primary roles here. And as we do operating and the controlling of the networks, obviously we're speaking to the people in the field who are doing the physical switching on the equipment, and we're just looking after them, their safety and safety of the plant. So to understand this problem, I think we really need to understand the size, and it's really the size of Eskom, the size of South Africa in the international context. If we have a look at our current fleet, we have 15 coal-fired stations. It's just about 39,500 megawatts. And that's quite an important number to remember throughout this presentation when we start talking about the failures and the size of the failures that we've been having. We've got 4 gas fueled stations. It's actually diesel fueled, almost 2,500 megawatts, Eskom owned. We've got 6 hydroelectric stations, and that's pretty much the potential of hydroelectric in South Africa. Of those 6, 2 of them make up the 600 and the other 4 make up the 61 megawatts, so they're quite tiny. We then also have pump storage. We'll talk about that, but about 2,700 megawatts there. We've obviously got the 1 nuclear power station being Kuberg. And then Eskom owns only 1 wind power station, 100 megawatts. That's the Siri power station on the west coast. We've also got 2 independent power producers. They are also open cycle gas turbines burning diesel, and they make up just over 1,000 megawatts of capacity. What you see in the gray there is all the renewables that have been added to the grid since December 2014. We're up now at about 5,600 megawatts of renewables that's been connected to the system. And I will delve into that in just a little bit of detail. I think that it's quite interesting to see where we are with renewables, what they are doing, and just to link up with some of the other presenters. I believe Prof. Van Niekerk yesterday was also talking about renewables. But let's just take a very slight detour and talk about the renewables. The bulk of the renewables in South Africa is wind generation, solar PV, and what we call CSP, or concentrated solar power. It's just a slightly different solar technology. And what you see in that top chart there is, that's actually for the month of September. You'll see there's a dark blue line there, which is representing the CSP output. We have about 500 megawatts installed, and I hope it's big enough on your screens. And you can see that that CSP pretty much as the sun rises, peaks in the afternoon and then drops off. They're reaching their 500 megawatt output. What's interesting about the CSP is that they do have storage capability. One plant actually has about 6 hours of storage. So that's very useful for us as we go beyond sunset. They are still able to generate. The green that you see in the background there, that's the solar PV. And again, you can see how very regular it is. It's very predictable in South Africa. There are very few days that we don't have high PV generation. Obviously peaking at noon and then dropping off towards sunset. The wind generation, a little bit more erratic. This is still somewhat a winter profile, but what we do tend to see in the summertime is a lot more predictable behavior from the wind generation, mostly because of the offshore winds that blow as the sun starts to set and we start to see the wind pick up. That's actually very useful for us because it coincides with our evening peak, which is the highest demand of the day. And because of that, it actually does help support the peak quite a lot. The bottom is exactly the same information, but again, it's stacked up one on top of the other. And you can see, almost consistently in September, we've been reaching 3,500 megawatts during the day of wind, PV, and CSP. And there have actually been days where we've been over 4,000 megawatts contribution from the renewables. What's interesting is we actually reached the highest renewable output was on Saturday last week, not this previous Saturday, the one before, where renewables actually accounted for just over 20% of what was being generated in the country and supplying the demand. So we may think of South Africa as still starting out on our renewable journey, but I do believe that we have significant amounts of renewables already installed on the grid. Saturday does tend to have a lower demand, and so the percentage contribution does go up. But typically during the week, we would see a contribution of about 12%. So it has become quite significant. I've got some statistics here. I won't go through all of them in detail, that you can read at your leisure when the presentations come out. Just to mention the one statistic that we do watch here at System Operator is in this bottom table on the bottom left. What we monitor is the change in the renewables from one 24-hour period to the next. So from one evening peak to the next evening peak, we look at the change in the output of the renewables. Now, that becomes quite important for us because as the renewables pick up or drop off, we are then required to dispatch generation to make up for that difference. And if you see on the 7th of August, between the 7th and the 8th of August this last winter, we actually had a delta of about 1,750 megawatts. To put that into perspective, that means that in a 24-hour period, we need to dispatch about 3 very large coal-fired generators. Right, going back to the theme of how big is the problem, I've just put it into the context of Southern Africa. And once again, I'm not going to go through every single number here, but just to highlight a few of them, if you have a look at South Africa, our demand is roughly 38,000, almost 39,000 megawatts. We have fallen a bit short of that in the last few years. Last winter, we had a demand of about 35,000 megawatts. But if you compare that to some of our neighbors, from the one extent where we've got Lesotho at about 150 megawatts, and then down to the next biggest in Southern Africa, which is Zambia, at about 2,200 megawatts, you can understand that the order of magnitude is just significantly different. And that brings with it 2 big problems. The first is that if South Africa does have problems, it generally means that the whole of Southern Africa has problems. You know, when you've got this big anchor power system shaking around, it does tend to shake the others loose. And the other problem is that when we do go into a blackout type of situation, there's not a lot of help to be offered from some of the others. All right, as I said, it's really important for us to keep the frequency at 50 hertz. This is the supply-demand balance. And it really comes back down to the mechanical capabilities of our generators. The really large coal-fired generators, they run at about 3,000 RPM. If you have a look at the turbine blades on the LP turbines, those tips of those blades are running over the speed of, over the sound barrier. They do run in a vacuum, which does help. But you can imagine that these devices are very high speed, very, very large. You know, I think large as in half a house size. And they are a lot more fragile than they actually appear. I mean, it's very large equipment, but they are running in very, very tight tolerance. The problem, and this comes from our grid code, and for those of you who are not familiar with the power industry, we are governed by the grid code, which is a NERSA document, NERSA being the National Energy Regulator of South Africa. And grid code is a suite of documents that describes how participants in the power system, we call them licensees, how they are to behave, what is required from them, what they're expected to be able to do, their capability technically. It dictates to the system operator exactly what is expected of the system operator to maintain the stability of the power system. And interestingly enough, I saw you talking about city power earlier on. There are also terms and conditions in the licenses from NERSA which dictate how people participate and what is expected of them during a crisis on the power system. So the main reason that we need to keep the frequency within a very tight band and within tolerances of technical design is because of these large turbo generators. The graphic that you see on the top right-hand side, it shows a number of ranges, and I'm going to actually start from the left-hand side and the right-hand side and move left. On the vertical axis, we've got the frequency, and then on the bottom, along the horizontal axis, that's the time, and it is a logarithmic scale. And you can see that for the most part, as long as we're keeping the frequency between 49.0 hertz and 50.1 hertz, we expect the generators to be able to operate continuously within that range. As we move towards the left-hand side, you'll see I'm going to concentrate on the lower frequency band, but we have similar problems in the higher frequency band. As we move towards the left, when we get to the range of 49 to 48.5 hertz, there are restrictions here. And over the lifetime of a large generator, where they were only expected to be able to tolerate those types of frequencies for about 80 minutes. A lifetime of the generator, typically around about 30 years. So you can see that there's quite strict tolerances already as we move just from 49 hertz down to 48.5. Moving then down in frequency, if we go between 48.5 to 48 hertz, the tolerances there in the design is only 10 minutes over the lifetime of the plant. So 10 minutes in 30 years is where they would expect to be able, be expected to operate. For those first two, there's no tripping instantaneously, but if we drop below 48.5 hertz, after 1 minute, we would generators start tripping. As we go further down in frequency at 48 hertz, we would then see that over the lifetime of the plant, they would expect only to be operating there for about 1 minute, and they would then start tripping seconds should we get down to those frequencies. And then below that, it just really gets chaotic. I mean, we're talking about 6 seconds, and below 47 hertz, we're talking about 200 milliseconds towards tripping. And so you can see that if we start to get into a situation where we don't have enough capacity to supply the demand, and that frequency starts dropping, we will start to get into these ranges, and we will start to then see generators automatically tripping off to protect themselves. Obviously, that then becomes a cascading problem. As more generators trip off, there's less demand or less capacity available to supply the demand. The frequency drops again, and so on and so forth. And you get into this cascading situation where you would then eventually trip every generator connected to the power system. Right, now, obviously, before we allow that to happen, we at the National Control Center will try and control this frequency. During normal operations, and I'm going to go through this graphic from the bottom up. During normal operations, we will dispatch power stations. So we've got the nuclear power stations, coal power stations, some of the renewables, although we don't dispatch them, they would be contributing to the system. And then, of course, some of the IPPs, those two OCT or open cycle gas turbine power stations that I was talking about. They will then be dispatched, and that's in a very slow sort of minutes to hours type of time frame. As things get a little bit more interesting and the customers demand more power, we start to then dispatch our own open cycle gas turbines. We start to dispatch some of the hydro stations and some of the pump storage stations. We have some interesting products that we've developed over the years. I must say, so I think South Africa is one of the leading countries in this aspect, probably out of desperation, but we've developed a number of very innovative products with our customers where under certain circumstances, they'll either manually switch off their plant. In some cases, we've got automatic switch off of their plant. In some cases, we've got contractual agreements with them that we can interrupt them from the National Control Center. And so instead of being able to bring more generators onto the system, we then will dispatch the demand response products, where we have these special contracts with customers to switch off either the entire plant or parts of the plant. And it's equivalent to bringing on an additional generator. The benefit we do have there is that it can come on really, really quickly. We have one customer who can offer us 450 megawatts instantaneously. To put that into context, a large coal-fired power station can ramp at about 8 megawatts per minute. So it's quite a slow process to ramp up those. Our hydro stations are a little bit faster, about 200 megawatts per minute. So they really can ramp quite quickly, but quite limited. Again, if I'm talking about that 450 megawatts, put it in context of size of some of those Southern African countries that we've just looked at. And you can understand that, you know, we're playing with very large blocks of either customer load or very, very large generators. We do have a demand response product. I'm sure you're all familiar with it on TV. When you see the power alert, you'll see either the green, the orange, the red, or the black, as you'll see today. And we still do get a response from the public when we appeal to the public. It does tend to have a bit of a tolerance on it, where if we're shedding for long periods of time, the public's tolerance does tend to wane. But if we haven't shed for quite some time, we get about a 275 megawatt response from the public, which is always, you know, we're always very happy to see that response when the system is constrained. Beyond that, we then go into an emergency, and there is a document, I'll talk a bit more about it later on. It's the National Code of Practice, NRS 048-9. And this is a document that was developed back in about 2012. I think the first version came out. And it's an industry document describing the do's and the don'ts and the rules around load shedding. We'll delve into that in a bit more detail just now. But that does require the system operator to declare a power system emergency, which we then do. And then we go into the stages of load shedding. I'm sure you were all shocked and horrified when the second edition of NRS 048-9 first came out and started talking about load shedding stages from 1 to 8. We were all familiar with 1 to 4, and then suddenly 8 came up. And those of you who remember the 9th of December 2019, we actually did have to implement stage 6. So the document does set out a very systematic, a very controlled way of doing load shedding. And we are bound by that. It is actually a NERSA approved document. So the operator is bound by that document. And that's how we carry out the load shedding. Heaven forbid we ever need to go beyond stage 8, but we do have contingency plans on how we would go about doing that. It's a little bit more chaotic. The blocks that we would have to throw off in that type of emergency are much larger. And whereas the load shedding is actually carried out by the regional control center at quite a localized level, the thing beyond stage 8 would actually be carried out by national control. And literally, we would be throwing towns and cities off at a time, not suburbs. We would be able to sustain that for quite some time, but there is also a limit that we can maintain an interconnected power system and remove all of that power. So it does have limitations. And just in case you are wondering, there are contingency plans beyond that. That's outside of the scope. Right, now, obviously, things happen quite quickly, as we saw last night. Within half an hour, we lost 2 very large generators, and that's what forced us to bring the load shedding forward to 1800 last night. But things can happen extremely quickly. We've had a number of examples over the years where we have lost an entire power station, so up to about 3,600 megawatts disappearing within less than a minute. Obviously, a human operator cannot react fast enough to try and mitigate against that. And so we have extensive protection schemes, particularly in the under frequency domain, where we can actually automatically remove customer load from the network and just try and stabilize it. What you see this graphic in front of you now, we have the green portion, which is what I've just described. This is kind of normal operations where things happen fairly slowly, minutes to hours, and we dispatch various generation and demand response products. We then have a first breakpoint at 49.5 hertz, and that's where we would automatically start up some of our generators if they had not started already. Again, I'll come to the pump storage now, but those are some of our go-to plants. Remember I said that they can ramp extremely fast. So we do automatically start those at about 49.5 hertz. With the frequency continue to drop, we've then got 3 stages of automatic, what we call under frequency load shedding. And these are physical relays that are they're actually installed mostly in customer plant, where they would automatically sense a drop in frequency and they would then trip the plant that is connected to them. So similar to something that you'd find in your DB at home with an under frequency capability. We've got 3 stages connected there. The first one triggers at 49.2 hertz, the second one at 49.1 hertz, and then the third one at 49 hertz. And you'll remember from that graphic that I showed you around the capabilities of turbo generators, that 49 hertz becomes quite an important breakpoint for us as well. Connected to each one of these, what we call stages, we've got about 3.3. So by the time we get to 49 hertz, we've disconnected about 10% of the load in the country. And that happens in less than a second. If we go any deeper than that, at 48.8 hertz, we start to do much bigger blocks. And we have then 4 blocks of 10% each, so really large chunks of load that would come off. And that would start tripping between 48.8 hertz all the way down to 47 hertz. In total, we've got about 50% of the load on the power system connected to this system. And so within literally less than a second, we could disconnect 50% of the power system. That sounds like a great plan. What does tend to happen is because our power system is quite vast and very high voltage, we would have tremendous disturbance in the voltages, and obviously the frequency is already disturbed. And so it would be, the power system would be in somewhat chaotic position at that time, which we would have to then try and rectify. But if we're quick enough, we would be able to stabilize the voltage, bring it back up to 50 hertz by removing these blocks of load. Right at the bottom, you'll see, and that's the topic of what we're going to speak about next. Should we fail to remove sufficient load, or if we have the cascading generation tripping that I was talking about, we would then go into a national blackout. And this is really the part that we need to understand. This is what we are doing when we are load shedding. We are trying to avoid this blackout. All right, so I think first up, we need to understand that it's not just a lack of generation capacity that causes national blackouts. In fact, system operators around the world do similar things to what we do. You know, they have contingency plans, they dispatch generation, they have under-frequency load shedding, and all the precautions that we take. In general, what we find is that large blackouts actually start on the transmission system, where you have a fault on the transmission system. Usually that would disconnect a generator, and then from there we would get some sort of cascading events. We've had a number of blackouts around the world. I must say, touch wood, that in South Africa we've never had a full blackout of the power system. In the early 90s to mid 90s, we did black out the Cape Province, sort of from De Aar down. We did black that out a few times. We also islanded, where what happens is we actually did manage to sustain it's separated from the main grid, and then we managed to sustain an island in the Cape, which we could then quickly reconnect back to the main grid. So that's the closest that we've come. It's also during those instances that we had the operation of the under-frequency load shedding, where we did get down to about stage 3. So we removed about 10% of the load on that island, but we have never had beyond stage 1 under-frequency load shedding on the main grid. So in other words, as soon as the frequency got down to 49.2, and we have had a number of those instances over the last 10 years or so, we would automatically remove that load, and it's so fast that it does actually recover the frequency back into normal operating range. You can see I'm not going to go through every single one of these. Number of blackouts around the world, most of them making headlines. The most recent one that made headlines was one in Texas. I'm sure you all saw that. But the one that really struck me and drew so many parallels with South Africa was the one that happened in Venezuela. That was in March 2019. You can see the duration there is given as 5 months. It's given as 5 months. We don't anticipate being off for 5 months, and I think that's somewhat of an exaggeration. They did re-energize their network well within that time period. But why it's interesting to us, they have a similar system to us, and you also see that the cause given for their blackout is poor maintenance. There was a wonderful article, and I remember living through this at the time. You know, I wake up every morning just to see what the progress was being made in Venezuela. There was a wonderful article written. The reference is at the bottom there, and I do urge you to go and just read up on that. It's a fairly short article, not a big read, but it does draw a lot of parallels with South Africa. I've just taken some of the extracts from that. Let's start with a picture that, and again, it is probably quite small on your screens, but what you'll see is quite a large crowd gathered there. And this was in Caracas on the 11th of March, where it is actually a sewage canal, and you've got people lining up with buckets both at the top and at the bottom, collecting raw sewage water because they had run out of water. We also obviously have the sporadic looting that happens. You saw in most cases around the world where there is a blackout or a partial blackout, it does tend to be followed with a lot of looting. You can use your imagination in South Africa, if we had to go into a full blackout, there's no doubt in my mind that there would be extensive unrest, extensive looting. My predecessor said that it would be equivalent to having a civil war in the country, because what's left after the blackout would be similar to what's left after a civil war.
We also then have, obviously, all the horror stories of the morgue. Can't keep the bodies of the deceased cool. We have a number of reports of people who have passed away because the hospital maintain various equipment. But I think the quote at the bottom where it says that the impact is devastating on almost every single part of daily life. And this really does need to be understood to appreciate why we need to load shed. In South Africa, we also have a unique situation where at any given moment in time, we have thousands of people underground in our deep level mines. And while we do have backup generators and we work with the mining fraternity to make sure that those backup facilities are available, there is always that possibility that we strand thousands of people underground. And I don't think it's being over dramatic to say that should we ever black out this power system, we would lose hundreds to thousands of people's lives. Right, some of the things that would happen during a blackout, and really this is just the tip of the iceberg. The telecommunications, obviously, that would be severely affected. Our best guess is that the mobile sites would be available for hours. Many of you, even during load shedding, your cell signal drops off after about 2 hours. And when we go to stages 3 and 4, you start to see that those cell phone towers die even quicker than that. We would start to see the backbone of the telecommunication systems fail in about 8 hours. Obviously, a lot of them run on batteries. Those batteries would deplete quickly. The one that I think is the most devastating is that our water reserves would be severely impacted. And it's not only on the water side, but you can imagine if we don't have pumps to pump sewage, that would become quite a messy affair as well. So we've got about a 48-hour guideline that we put in place for municipalities. Unfortunately, that's not across all the municipalities. We would struggle to distribute raw water. Our data centers, and South Africa has become quite popular. We're very large data centers. Where we're situated in the world is quite convenient. Stepping into Africa, the data centers would most probably start failing due to a lack of water. They take quite a bit of water for cooling. And then at the power stations, obviously, they utilize quite a lot of water. Unfortunately, most of those pumping stations would not be impacted immediately. Some of them would have capability, but after a while, they would go down. Obviously, no MS Teams. I think for some that would be, in this case, Zoom. For some that might be a blessing. We also anticipate that we would have a really, really big problem with liquid fuel. And again, not only just to run our diesel generators, but also the rest of the country. Movement around the country and transport around the country would become severely limited. In terms of security, I think you can just let your imagination run wild. But what we are 100% certain of is that we would not be able to rely on the national security structures. They would have their hands full. And so there would be very little help for the municipalities and for Eskom and for some of the other essential services. That's really just a glimpse into what it would be. The closest way I could explain a blackout, and this really doesn't do it justice, is to say that it would be the equivalent of stage 35 load shedding continuously and simultaneously across the country. It's a very different story when you're being shed and you can go to the next suburb and buy food, or get takeaways, or you can wait 2 hours for the lights to come on. The anticipated timeframes that we're dealing with here are about 6 to 14 days. All right, so I hope that I've sufficiently scared you, and before you all say that this is a disaster waiting to happen, we certainly don't leave it up to luck. There is an enormous amount of work that does go into preventing and dealing with a blackout. Again, I will leave this in the pack for when you get the presentation, you can have a look at it at your leisure. But all the way from the time that we actually start designing the power system, we're already building in contingency plans, we're building in capability to prevent blackouts. The way that we actually operate the system, we always have contingency plans in mind, one of them being the load shedding. And that's what you would see there in this Swiss cheese model or accident model. One of the barriers that we're talking about today is this manual response. We also then have, as I described earlier on, the automatic protection. And then once we do go into a blackout, obviously trying to put it all back together would take some time. And in our case in South Africa, it's quite technically challenging. Right. So when we have a blackout across the country, we would have to restart the country. And this is the equivalent of rebooting your computer. So basically what we do is we start up one generator. It takes, to start up a big Medupi generator, takes about 60 megawatts. Now, again, if you put that in perspective, Lesotho takes about 150 megawatts. To start one generator at Medupi will take 60 megawatts. We've obviously got to supply that from somewhere on the assumption that all the generators have actually been shut down or tripped. We then have facilities where we can automatically start them without any external assistance. We use that facility then to start up the coal-fired station. Once that's started up, we then start the next one and the next one and so on and so forth. Our topology, because we've got such a high voltage network and such a sparse network, it does make it technically challenging. For example, we would start a number of the power stations in the Witbank area, but by the time we have to energize to get all the way down to Cape Town, that is energizing an enormously long power system with very little support along the way. And so we'd have to come from a very strong base. So to build it, we'd have to build the interior network of the country to be fairly robust before we would actually be able to get down towards the Cape. We do have black start capability. We practice this very frequently. We have very detailed plans on how to do this. And in fact, just a couple of weeks ago, we did a dry run where we physically shut down a piece of the network and started up a little island and practiced on how to do that. So it is top of mind for the system operator. We do exercise on this regularly, but we also hope that we never see it in our life. All right, in terms of the timing, the nature of a large coal-fired generator is such that as it starts cooling down, it takes longer and longer to start up. So a generator that is hot, we call it a hot start, typically between 2 and 4 hours be the restart time. And now you can imagine if we're restarting one generator and then waiting to start the next generator, by the time we get to the next batch of generators, they would have cooled down again, so quite quickly, and that would then possibly be a warm start, where we would take between 4 and 10 hours.
Frozen?
Because is that a question?
No, I'm just saying that
can take up to
7 for a bit.
On best case. Nancy, sorry, I missed you there.
No, we missed you a bit because you were frozen.
Oh, okay. Am I back?
Yes, you're back.
Right, super. All right, so I hope you kept up with the timing that I was talking about. So our best case scenario, as I said, is 6 to 14 days to restart this grid, and that would be to get it back up to about the 30 gigawatts that we normally supply on any given day. All right, the next question I want to sort of get into is our emergency reserves. To understand our emergency reserves, we need to have a little bit more insight into how our customer demand behaves. We have very, very seasonal profiles in South Africa. The first one, which is a little bit easier to deal with, is the winter demand, and that's the graph that's in front of you. The bottom axis there is just the 24 hours of a day, and on the horizontal axis, we've got the megawatt demand per hour. And you can see that in the middle of the night, if we start off at about 3 o'clock in the morning, what we call our night minimum, that would be the minimum demand, and that ramps up very, very steeply towards our morning. The morning peak does vary, and it's very much driven by school holidays. So if we don't have school holidays, that peak is around about 6 o'clock in the morning. When there is school holidays, it's around about 9 o'clock in the morning. But I think the profile of the winter is really dominated by this enormous evening peak that we have here. That happens at about sunset, summer and winter. And you'll see if you look at the red graph, the summer evening peak has moved and shifted quite significantly as well. The other very obvious thing that you can see here is the red line for the summer demand profile is a lot lower, but a lot flatter. We don't have that valley and we don't have that very large evening peak. So this brings with it two types of problems. That orange line that you see there, just a hypothetical, if that's where our generation capacity availability was, I put that about 31,000 megawatts, you would see that we cut the evening peak in winter where we cannot supply what's above the orange line. And there we would either use the very expensive open cycle gas turbines, or we would use some of the demand response products I was telling you about. If we've exhausted all of those, we would then have to go into load shedding. And typically, this is what we see during the winter period. You will see a fairly short period of load shedding over the evening peak. In contrast, in summer, where we start to do quite a lot of maintenance on our generators, we've obviously got that lower demand, but because it's so flat, if we end up where we are at the moment, actually, around about 26,000 megawatt availability, you'll see that the area that we can't supply is quite significant, but it's also very, very patient. And this is exactly the problem that we've got ourselves into today, while we're shedding until Saturday. We've been using our open cycle gas turbines to supply the demand over the last few days, and we just haven't been able to lift that orange line, get that capacity up. And so we've actually got to a point now where we've exhausted our diesel reserves, we've exhausted our pump storage dam reserves, and we simply don't have enough power to continue doing what we have been doing. And that brings us to our emergency reserves. I'm sure those of you who read the media statements that come out, you probably think we sound like a bit of a stuck record, saying we're replenishing emergency reserves all the time. But this is exactly what's been happening and what continues to happen. To try and get a better understanding of that, I think we need to understand the cycle of our pump storage and our open cycle gas turbines. We have 3 pump storage stations in Gula, Drakensberg, and Palmit. And very simply put, we have a reservoir at the top of the mountain, we have a reservoir at the bottom of the mountain, we hollow out the mountain, and we put a generator and pump sets in between. And during the night, where we have that lower demand, we are then able to use that excess energy and we pump the water up to the top reservoir. And then obviously during the day, when we need the energy, we can then generate with the same plant. We have about 168-hour cycle between pumping and generating, so over 168 hours over the week. That cycle goes from full dams on a Monday morning to, let's say, empty dams by a Friday evening. We then top it up over the weekend and we're back to where we should be on a Monday morning. That's if everything goes to plan. If we have to utilize this resource a lot more during the week, then obviously we deplete that resource much faster and we can't replenish it. We can't get to the weekend. The second technology that needs to be understood is our open cycle gas turbines. We have 20 of them in all. Eskom owns 14, and there are 6 privately owned. And I think it's an understatement to say that these things guzzle. The consumption of one diesel generator at full output is consuming about almost 1,900 liters of diesel per minute per generator. When we run all 20, you can imagine how much diesel we are using. And that brings with it 2 problems. First of all, the cost is horrific. It's about 10 times more expensive than utilizing coal. But the second problem is that we simply cannot move diesel to these generators fast enough. So even if we have the diesel available, you can't get it to the power stations to sustain them for 24 hours a day. The other problem is that by using this amount of diesel, we deplete the country's reserves quite rapidly. So anybody living in Durban, you might have noticed that there's a bit of difficulty getting diesel. That should normalize today. But over the past few days, there has been a bit of a lack of diesel in Durban. Right.
So our emergency reserves, we do class the pump storage as emergency reserves when we run like this. They were not originally designed to run like this. As I said, they were designed as peaking plant, but desperate times calls for desperate measures. The OCGT is obviously constrained by the diesel, not only what's available in the tanks at the power station, but also getting it to the power stations. All right, to give you an idea of the size, in the pump storage, we've got about 2,700 megawatts between the 3 power stations. For the open cycle gas turbines, there's just over 3,000 megawatts. And I think to understand what happens when we run out of emergency reserves, if you add those two together, that's almost 1,000 megawatts. One stage of load shedding is about 1,000 megawatts. So if you run out of diesel and water, that's already six stages of load shedding on top of all the other shortages that you may have. So you can imagine that we protect and we preemptively load shed before we deplete these completely. And that is exactly what we're doing now. If we had continued running our OCGTs and running our pump storage, by sometime this afternoon, we would have run out and we would have then had to go to stage 6. If we look at some of the others, you'll see that we do have those contractual agreements that I talked about where we can interrupt 450 megawatt blocks. There's about 2,000 megawatts there, and then we have some other customer demand. But they are really limited, mostly to about 102 hours we can utilize them. So the heavy lifting really does get done with the pump storage and the OCGTs. Right. A very quick word, because I am aware that I'm starting to run out of time. How we actually manage this process, as I said to you, we've had to become quite innovative in Eskom. We've had to manage the power system very differently from the traditional way of doing it. When we work with the generation colleagues, obviously we need to do maintenance on generators, but we can't shut them all down because we would have to shut down the network. And so we have been forced to do maintenance as and when we can. We're trying to do it as aggressively as possible to try and fix the plant, but obviously we have to balance that with being able to supply at the same time. The system operator works with the generation group, and we then look at what's required. We do a number of optimizations and iterations in the outage plans. And then we take that outage plan and we do some scenario planning on it. And this is one of the differences from us to the other system operators around the world, where we've had to now go to scenario planning. And it does make it sound as if system operators being very elusive about what's going to happen. You know, you never seem to get a straight answer out of us. And I'll show you some of the reasons for that now. So we've been forced to do some, take into account some of the emergency reserves that we do have, and then do scenario planning. The plan is actually a very simple arithmetic plan, but like your paycheck at the end of the month. You start off with a very high number at the top, which in this case is the installed capacity. You subtract your unavailability of plant, which is the sort of pinky color that you can see. We as system operator, we look at three scenarios for that. We look at a 12,000 megawatts of UCLF, so UCLF being the unplanned capability factor. We look at 13,000 megawatts and 14,000 megawatts. To give you an idea, our base case is 12,000. That's where we thought we might be running. Last week, for 1 hour in the week, we hit 16,000, and last night when we tripped both of those generators, we actually got to just over 15,000, and by this morning we were at about 13,500. So that number varies a lot. And while we interpret these scenarios, it's important to remember that we never actually operate in a single scenario all the time. It's a blend of the scenarios, and we move to and from different scenarios as the generators become unavailable. We also do make an allowance for planned outages. We then also make an allowance for operating reserve. That's really the reserve that system operator retains as part of our contingency measures to react to instances on the power system. We've then got the OCGTs, and again, we've separated those out simply because they are so horrifically expensive, and then that leaves the capacity available. This black line that you see, that is the expected customer demand over the next 18 months. And you'll see that we are running mostly in the area where we are running gas turbines or diesel generators for significant amounts of time.
And we even get into a point where we get into this yellow area, and as we go into the yellow, that's where we start to find load shedding. So to give you an idea of how we've been performing over the past winter and the past summer, we have a histogram here. Across the bottom is the unplanned unavailability, or the breakdowns in megawatts. Across the top, across the horizontal axis is simply the frequency, or the percentage of time that we've experienced that level of breakdown. You'll see in the background, shaded in the background, you've got 3 different colors. Those are the 3 scenarios that System Operator had a look at for winter and for summer. And let's look at last winter. That's the one that's just gone by now. And you can see our planning scenarios, we were in the base case about 17.8% of the time we operated there. We then went 24.1% of the time we were between 11,000 and 12,000 megawatts of UCLF, and then so on and so forth. What's alarming is the amount of time that we actually spent beyond our planning criteria. People thought that we were being overly pessimistic, setting our base case at 11,000 megawatts. As it turns out, we weren't pessimistic enough. The other thing that is really striking on this histogram is that we have a range of UCLF and unplanned unavailability from 7,000 megawatts up to 17,000 megawatts. Right. That is an enormous variance. In a single week, it's not uncommon to have a variance of about 4,000 megawatts. Now, again, if you go back to our peak demand of 35,000 megawatts, it's more than a 10% variance. And if we put it into context against the renewable generators, which the rest of the world says really unreliable and unpredictable, in South Africa, we would expect an error on our renewable forecast of around about 250 megawatts. Yet on our coal fleet, we are dealing with an uncertainty or an unreliability of 4,000 megawatts. The reason that I'm hopping on this is really, it goes to explain why we can't give certainty to the country of when we're going to load shed. These things happen all of a sudden. Again, I used last night as an example, where you seem to be fine going into an evening peak, and then all of a sudden you have 1,300 megawatts disappear in front of your eyes. And then there you have to take action. And obviously last night, the load shedding that had to be implemented. But the system really is volatile. It really is extremely unreliable. And because of that, as I say, we've been forced to do the scenario planning, but it also makes giving the country certainty absolutely impossible. There are some rules. As I say, we are governed by grid code. We are governed by NISA. The NRS 048-9 edition 2, that is a NISA approved document, and it sets out the rules and regulations for the entire industry. I think the most important thing around this document is the sentiment that it says everybody on the power system must be treated equitably. Now, this document was written by industry. It wasn't written by Eskom alone. And it goes to looking at the critical loads, the essential loads. So, for example, a critical load would be a coal mine supplying a power station. Obviously, during load shedding, you wouldn't want to shut down a coal mine because then you would just exacerbate the problem. But you also get essential loads such as hospitals, which are not excluded from load shedding. However, there is criteria for them to meet. So they must have backup generation and whatnot. But if there is a failure of their backups on that particular day, there are communication channels available to them where we could temporarily give them back supply in the interest of saving lives. And that's all laid out in this document very, very clearly. How we actually physically do it. The system operator, we obviously then monitor the power system 24/7. As soon as we encounter a constraint, we determine whether what stage of load shedding is required, what duration is required. If there's enough time, we try and give the country as much warning as possible. You'll see the media statements will come out. If there's no time, we are fully mandated to do whatever is required at any point in time to stabilize the power system. You'll notice last night that happened all very, very quickly. We were supposed to start shedding at 2100 last night. That was very quickly brought forward to 1800. We also do have a mechanism where we can issue early warnings and alerts, and that's really to get the regional and the distribution control centers ready. My connection is playing up again. I hope you can still hear me. So we give an early warning so that we can get them ready, because in the distribution and the municipal control networks, load shedding is really hard work. Rotating all of those blocks of load every hour, every 2 hours, or whatever the case may be in whichever area, it takes an enormous amount of focus and amount of attention. So that is to get them ready and get them going with the load shedding. As I said before, we instruct the load shedding to be done at a regional level, and that's then carried out by the municipalities and the distribution, and then obviously we carry on monitoring and seeing how things develop from there. Right, some of my final thoughts. I think by now, I hope I've illustrated 2 different reasons for load shedding. Typically, when we have a very high peak demand, and that happens in winter, we simply don't have the capacity to supply it. Even if we run all the diesel generators and the pump storage generators, we simply run out of capacity. The second reason, and that's much more common in summer, where we run the diesel generators and the pump storage extremely long and extremely hard, and eventually we run out of fuel at those stations. And before we start running out of fuel and going to stage 6, we then start rationing that fuel, and that's exactly what we're doing today. And then perhaps as my parting comments, we do only implement load shedding as a last resort. I think it's clear to everyone now. We are trying to avoid a national blackout, which would be infinitely more chaotic, more dangerous, consume more lives than load shedding. It will take us somewhere between 16 and 14 days to restore if we go into a blackout situation. So it is far better just to disconnect the customers from a healthy network, or get the network into a healthy state so that we can relatively quickly reconnect. Again, I know that the anger around load shedding is there. Believe me, I'm also angry as a consumer. So I hope that I don't think I would have taken the anger away. And let's be honest, I mean, we have a right to be extremely angry about what's happening in Eskom at the moment. But I do hope that I have given enough information to give a level of understanding where we may possibly have eased the frustration. That's it.